this video, we're going to look at the sum and difference identities for sine and for tangent. So hopefully at this point, you've already watched the video for the sum and difference identities for cosine. So we're kind of familiar with the idea of what our goal is. We're going to be taking a given angle that's not on the unit circle and trying to write it as the sum or difference of two angles that are on the unit circle. Find the exact value of each expression. Again, anytime you have directions that imply or that indicate that you should give an exact value, do not grab your calculator. That's going to lead you down the wrong path. So we want to make sure that we're using our unit circle and our knowledge of the unit circle to find these, to evaluate these expressions. All right, so sine of, oh, I should leave those up. Sine of 75 degrees. So thinking of two angles from the unit circle that we could add to get 75 degrees or subtract. We can always use subtraction too. For me, it's oftentimes a lot easier for me to think about it in terms of addition, but that's not always the case. It just depends on truly the moment, the day, the examples I've already worked on, things like that. So 75 degrees, this is 30 degrees plus 45 degrees. Looking above, applying that sum formula for sine. This is sine of 30 degrees, cosine of 45 degrees. Plus cosine of 30 degrees times sine of 45 degrees. Using my quick sketch to determine those ordered pairs, 30 degrees is right here. So that's creating that longer, flatter triangle, making the x value the larger side. So my ordered pair is square root of 3 over 2. One half. And then 45 degrees, that ordered pair, since the x and the y are the same, square root of 2 over 2, square root of 2 over 2. Sine of 30 degrees is 1 half. Cosine of 45 degrees is square root of 2 over 2. Plus cosine of 30 degrees is square root of 3 over 2 times sine of 45 degrees is square root of 2 over 2. This is square root of 2 over 4 plus square root of 6 over 4, or square root of 2 plus the square root of 6 over 4. Tangent of 7 pi over 12. Breaking down 7 pi over 12, I'm going to think about this as 3 pi over 12 plus 4 pi over 12. And before moving forward, I do want to make sure that those two fractions simplify to give me values from my unit circle. So this is tangent 3 pi over 12 simplifies to pi over 4. 4 pi over 12 simplifies to pi over 3. So check there. Looking above, the formula for the sum formula for tangent is tangent of A plus tangent of B divided by 1 minus tangent A tangent B. So again, we have our A and our B, pi over 4 and pi over 3 respectively. So this is going to be tangent of pi over 4 plus tangent of pi over 3 divided by 1 minus tangent pi over 4 times tangent of pi over 3. All right, pi over 4 in that first quadrant. That ordered pair is square root of 2 over 2, square root of 2 over 2, which tells me that tangent is 1 because the sine and cosine values are the same. pi over 3. That's my taller triangle. The y being the larger leg, the x or the horizontal being the shorter leg. So 1/2 is my x coordinate, square root of 3 over 2 is my y coordinate. Tangent of pi over 3 is sine over cosine, so square root of 3 over 2 divided by 1/2, which simplifies to just square root of 3 because those factors of 1/2 will simplify to 1. So again, just illustrating that we don't have to have these trig function values memorized. With more practice, this type of a sketch and deriving these values becomes very quick. So if you are like me, where memorizing a bunch of values is not going to be efficient or effective, this might be a great option for you. If you haven't watched my video on how to derive these trig function values, this might be a little bit confusing for you, so you might want to look back at it. But really, however you know the ordered pairs from your unit circle is absolutely fine, as long as you're able to access them and use them quickly. All right, so going back to my expression, tangent of pi over 4 is 1 minus tangent of pi over 3 was the square root of 3. Oh, I'm sorry, this is plus square root of 3 over 1 minus tangent pi over 4 is 1 times tangent pi over 3 is the square root of 3. So this is 1 plus the square root of 3 divided by 1 minus the square root of 3. And we've seen a lot of expressions where we've had to rationalize the denominator when we have one radical in the denominator. Let me be more specific. When we have a single term in the denominator that is a radical. Here we have a binomial in the denominator that contains a radical. So to rationalize the denominator here, we're going to use the technique of multiplying by the conjugate of the denominator over itself. Now we want to multiply by the conjugate of the denominator because when we FOIL out the denominator, multiplying conjugates, the middle terms cancel out and we end up getting rid of that radical. So let's go through this a little bit more slowly just as a review. In the numerator, we're going to FOIL. So 1 times 1 is 1. 1 times the square root of 3 is the square root of 3. Square root of 3 times 1 is the square root of 3. Square root of 3 times the square root of 3 is 3. Or, well, it's the square root of 9, which simplifies to 3. When we square a square root, those operations cancel each other out or undo one another. In the denominator, 1 times 1 is 1. 1 times the square root of 3 is the square root of 3. Negative square root of 3 times 1 is negative square root of 3. Negative square root of 3 times the square root of 3 is minus 3. In my numerator, combining like terms, 1 plus 3 is 4 plus 2 square root of 3. And in the denominator, we can see that those middle terms cancel each other out, leaving us with 1 minus 3 or negative 2. So here we have now gotten rid of that radical in the denominator, and now we just need to simplify this fraction. Both the numerator and the denominator have a factor of 2, so I'm going to actually show that factoring. So we're going to pull out a factor of 2 from the numerator, and this is going to be 2 plus the square root of 3, and this is divided by negative 2. 2 divided by negative 2 is negative 1. And then we'd want to distribute that. So this is negative, oops, I'm sorry. This is negative 2 minus the square root of 3. Cosine of 40, sine of 40 degrees times cosine of 160 degrees minus cosine of 40 degrees, sine of 160 degrees. Looking at our formulas, we want to basically see from the other direction if we can rewrite this expression as something a little bit simplified. So looking at this, the sine of one angle, cosine of another angle, cosine then sine. So we have a sine and a cosine, cosine and a sine in both of these. Now we want to pay attention to the sign. If it's plus between those two terms, this is the sum formula for sine. If it's minus, it's the minus or the difference formula for sine. Since it's minus, we're going to combine this as sine of 40 degrees minus 160 degrees. That is the same as sine of negative 120 degrees. Now we can use those even odd properties that we saw in a previous video. Since sine is an odd function, sine of negative 120 degrees is the same as negative sine of positive 120 degrees. Now thinking about 120 degrees, okay, with degrees, I think that using my tool for like counting fractions is a little bit trickier, but I know 120 degrees is going to be between 90 and 180. So it's in my second quadrant and it's going to be closer to 90. So if I think about it, it's going to be somewhere over here, 90 to 120. This is my 30 degrees. Oops. So we know that this is 60 degrees. So it's that long, tall triangle where the horizontal leg is going to be the shorter distance, so 1/2, and it's going to be negative because we're in quadrant 2. And then the vertical leg is the longer side, so square root of 3/2, and it's positive because we're in that second quadrant. Sine is that y value. So sine of 120 degrees is square root of 3/2. So this is negative square root of 3/2. Verify that sine of 180 degrees minus x is equal to sine of x. So starting with the left-hand side, we're going to rewrite it using our difference formula for sine. So this is sine of 180 degrees cosine of x minus cosine of 180 degrees sine of x. And we want to verify that this is equal to sine of x. 180 degrees, that's that negative x-axis. That ordered pair is -1, 0. Sine of 180 degrees is 0 times cosine of x minus cosine of 180 is -1 times sine of x. 0 times cosine of x is 0. And then when we subtract a negative, that's the same as addition. So this becomes positive sine x equals sine of x. All right. Suppose that A and B are angles in standard positions such that sine of A is 4/5 and cosine of B is -5/13. A is in quadrant 2, B is in quadrant 3. Find each of the following. Sine of A plus B, tangent of A plus B. So let's just rewrite these expressions using those sum and difference well, in this case, just sum identities for sine and tangent. So sine of A plus B can be written as sine of A cosine of B plus cosine of A sine of B. We have sine of A and cosine of B, but we don't have cosine of A or sine of B. So we're going to need to do some work to figure out those other two trig functions. Let's go ahead and rewrite tangent of A plus B. This is going to be tangent of A plus tangent B divided by 1 minus tangent A tangent B. And over here in my margin, we're going to set up those pictures for angle A and angle B. Angle A is in quadrant 2, so I'm going to emphasize quadrant 2 here. and sketch just a triangle inside quadrant 2. So here's my angle A. We're told that sine of A is 4/5, so that's going to be opposite over hypotenuse. To find that horizontal leg for angle A, couple things we want to remember that horizontal leg is going to be negative because we're in the second quadrant and x is negative in that second quadrant. And you might recall from a previous class these special right triangles or these Pythagorean triples that are just commonly seen whole number side lengths that are used for right triangles all the time. If you do, we would remember a 3, 4, 5 triangle, but if not, we're going to use the Pythagorean theorem and that's no problem. So we have 5 squared or 25 is equal to some x value squared plus b 4 squared or 16. Subtracting 16 from both sides, x squared is 9. And then x here, when we take the square root of 9, we actually get 2 roots, +3 and -3. But because of the position of this triangle, x is going to be -3. Okay. Now let's sketch angle B, which is in the third quadrant. So emphasizing my third quadrant. We're given that cosine of B is -5/13. So our hypotenuse is 13. And because we're in the third quadrant, x is going to, or cosine is going to be negative, or that x value is going to be negative. So here's our -5. Cosine is adjacent over hypotenuse, so just be careful that we're labeling the triangle correctly based on the trig function value that we're given. This is going to be another Pythagorean triple, and with more exposure, you might start recognizing these patterns and remembering them, but don't forget that the Pythagorean theorem is always an option for finding that third missing side length of a right triangle. So we have 13 squared is 169 equals -5 squared or 25 plus our y value squared. Subtract 25 from both sides, we get 144 equals y squared. When we take the square root, we get 12, but this is going to be negative because we're in that third quadrant. So now we have our 2 triangles completed. We can find all 3, well, yeah, all 3 of these trig function values for either A or B. So working on this example, sine of A plus B, which I'm just realizing is labeled incorrectly. They're both example B's. That's all right. Sine of angle A, opposite over hypotenuse, this is 4/5. Cosine of angle B is adjacent over hypotenuse, so -5/13. Plus cosine of A, adjacent over hypotenuse is -3/5. Sine of B, opposite over hypotenuse, -12/13. Simplifying these, we get -20/65 plus -3 times -12 is +36/65. And then combining these, we get 16/65. Tangent of A, tangent is opposite over adjacent. So tangent of A is 4/-3. Plus tangent B, opposite over adjacent, -12/-5. Since they're both negative, you could opt to just make this positive. And to avoid dealing with those negatives, which are simplifying anyway. Over 1 minus tangent of A was that 4/-3 times tangent B 12/5. Now I'm going to simplify the denominator here. So, and kind of clean up the numerator. So this is -4/3 plus 12/5. That negative, because it's a single digit in the numerator, single digit in the denominator, we can move that negative to the numerator. We could put it out front, but the numerator is kind of the most common position for that. I think it makes it a little bit easier to work with. Divided by 1 minus, and now I'm going to multiply these two fractions. Because the fraction, if I'm looking at -4/3 times 12 over 5, this is going to be negative, but when I subtract a negative, it's going to be positive. So I'm going to go ahead and clean up my sign here. This is going to be 1 plus 4 times 12 is 48 over 15. Now here's a really complex fraction. We can go step by step, getting a common denominator in the numerator, a common denominator in the denominator, and then use that, if we're dividing two fractions, multiply by the reciprocal of the denominator. But we could also clear and get one, or clear this complex fraction by multiplying the entire fraction by the LCD of all fractions over itself. So if I look at my three different denominators, this one is really 1, which isn't going to impact this. We have 3, 5, and 15. If I think about those three numbers, or those three denominators, the least common denominator is going to be that 15. So what I'm going to do is multiply my numerator by 15 and my denominator by 15. So in my numerator, I need to make sure I distribute that 15 to both fractions, and the denominator, same thing. We need to distribute it to both terms. And I'm going to write this out. So I've got 15 times -4 over 3 plus 15 times 12 over 5 divided by 15 times 1 is 15 plus 15 times 48 over 15. This step is really helpful in just making sure we don't make any, I call them brain farts, these baby minor mistakes that we happen to make when we rush. It just allows me to simplify each term individually without losing track of where I'm at. So 15 over 3 is going to simplify to 5. 15 over 5 is 3. And then 15 over 15 is 1. So in this numerator, I've got 5 times -4 is -20. Plus 3 times 12 is 36. No more fractions at all in the numerator. I've cleared them out. 15 plus 48 in my denominator. -20 plus 36 is 16. 15 plus 48 is 63.